You know, when you look at a periodic table, it's easy to just kind of gloss over that big chunk of elements right in the middle. But that is a huge mistake. That's the D and F block, and trust me, it's this mysterious, powerful kingdom that is way more important than you might think. It's kind of the engine room of our world.
All right, so let's get right into it. We're calling this the heart of chemistry for a reason. I mean, think about it. We're talking about the iron that literally builds our cities, the gold we've valued for centuries, all the way to the super specific rare earth elements that make your smartphone work. This block of elements has been shaping human history from the very beginning.
So, here's the game plan for this explainer. We're going to start with their place on the table, then dig into the secret of the d orbitals. That's the key to everything. After that, we'll look at their awesome superpowers, a few weird exceptions to the rules, a really strange F-block anomaly, and finally, tie it all together to see how these elements build the world around us.
Okay, let's kick things off. This middle part of the table, this is the home of the transition metals. And yeah, that includes some real heavy hitters, the ones that are super important for industry. Titanium, copper, platinum. They all live right here, acting like this perfect bridge between the super reactive metals on the left and all the nonmetals over on the right.
All right, now we're getting to the core of it. The secret of the d orbitals. Seriously, if you understand this one thing, it's like having a master key. It unlocks why these metals behave in all the weird and wonderful ways they do.
Which of course leads to the big question, right? We throw this term transition metal around all the time. But what does it actually mean? Like, what's the official rule that gets you into this exclusive club?
And here's the answer. The official definition comes from IUPAC, the folks who make the rules in chemistry. And it's surprisingly simple. A transition metal is any metal that has an incomplete d subshell. That's it. A d subshell that isn't totally full of electrons. That one little detail is the source code for all their amazing properties.
Let's make this super clear with a quick comparison. Look at scandium. It has just one electron in its d orbital, so it's not full. Boom, it fits the definition. It's a transition metal. But then you have zinc. Its d orbital is totally packed, 10 out of 10 electrons. So even though it lives in the d block, it technically isn't a transition metal. And that little distinction, it explains so much about why zinc acts the way it does. And just when you think you've got the rules down, things get a little weird. See, nature loves stability. And it turns out that having a d orbital that's exactly half full or completely full is a super stable state of being. So stable, in fact, that elements like chromium and copper will do something sneaky. They'll actually poach an electron from their outer s orbital just to get to that stable state. It's like they're bending the rules of physics for a better energy deal. Okay, so now that we know the rule, that all-important incomplete d orbital, let's look at the consequences. Because this isn't just some boring textbook definition. It gives these elements a whole set of chemical superpowers that you just don't see anywhere else on the table.
Superpower number 1. They're basically chemical chameleons. Because they can lose different numbers of those d electrons, they can have a whole range of different oxidation states. I mean, just look at manganese. It can be a +2, a +3, +4, all the way up to +7. That kind of flexibility makes it a total powerhouse in chemical reactions.
Next up, their second superpower, color. It's all because of those incomplete d orbitals. The energy gaps are just right for electrons to absorb certain colors of light when they jump between levels. The color that doesn't get absorbed is what bounces back to our eyes. That's why copper solutions are blue and nickel solutions are green. And it makes sense, right? If you have an element like scandium that's lost all its d electrons, there's nothing to absorb the light, and poof, it's colorless. They've also got magnetic personalities. Literally. The scientific term is paramagnetism, and it's all about having unpaired electrons spinning around in those d orbitals. A good way to think about it is that each unpaired electron acts like a tiny little compass. When you bring a real magnet close, all those tiny compasses line up and the whole material gets pulled in. It's pretty cool. And this isn't just a vague idea. We can actually measure it. The link is so direct. For instance, a manganese ion has 5 unpaired electrons, and we can calculate its magnetic moment to be about 5.92 Bohr magnetons. And what's wild is that when we go into the lab and actually measure it, we get almost the exact same number. The rule of thumb is simple. The more unpaired electrons you have, the more magnetic it's going to be. And their last big superpower? They are just plain strong. We're talking tough and stable. See, those d electrons get in on the action with the outer s electrons to form the metallic bonds. This creates this incredibly strong glue holding the atoms together. The result? Super high melting points, real hardness, and they're dense. This effect is strongest right in the middle of the block, where you find the most unpaired electrons available for bonding.
Okay, so we've got our main rule and the superpowers that come with it. But you know, chemistry, there are always exceptions to the rule. So let's take a look at a few elements that kind of push the boundaries and make us think a little harder.
This brings us right back to that weird case at the end of the block, group 12. We already pointed out that zinc has a full d orbital, so the question is, does that mean zinc, cadmium, and mercury all get kicked out of the transition metal club?
And yeah, if you're going strictly by the book, the IUPAC definition, the answer is yes, they're out. Their d orbitals are completely full, both as regular atoms and in their most common ions. They just don't have that incomplete d subshell that the definition requires. So even though we group them with the d block for convenience, they're not technically transition metals.
Okay, now let's go even deeper. Let's talk about that mysterious F block. You know, those two rows that are always pulled out and sitting at the bottom of the table? This is an even more exclusive club, and it has a really strange quirk that actually affects the elements that come after it. This strange effect is called the lanthanoid contraction, and here's the deal. As you move from left to right across that row, you're adding protons, so the nucleus gets a stronger positive charge pulling all the electrons in closer. Now normally, the inner electrons create a shield that protects the outer electrons from some of that pull, but the F electrons, they are awful at shielding, just terrible. So they don't block that pull very well, and the whole atom gets squeezed down, getting smaller and smaller as you go along, even though it's getting heavier.
And the result of this is just bizarre. Check this out. Look at zirconium and hafnium. They're stacked right on top of each other in the periodic table. Hafnium has way more protons and neutrons, so you would absolutely expect it to be a much bigger atom. But it isn't. It's almost the exact same size. Why? Because that lanthanoid contraction squeezed it down right before it was formed. This makes them act like chemical twins, and it is a nightmare trying to separate them chemically.
So, we've covered the rules, the superpowers, and even the weird anomalies. For this last part, let's bring it all home and see how all this quirky chemistry is the reason these elements literally build the world we live in.
When it comes to industry and construction, their strength is everything. I mean, iron gives us steel, which is the backbone of, well, everything. And when we mix in other transition metals like chromium or nickel, we get amazing alloys like stainless steel. That color superpower, it gives us pigments, like the super bright white in paint from titanium oxide. And of course, zinc, nickel, cadmium, they're essential for the batteries that run our lives.
And remember that chameleon superpower, the one with all the different oxidation states? Well, that also makes them fantastic catalysts. They can swap electrons back and forth, helping speed up chemical reactions without getting used up themselves. This is absolutely critical for huge industrial processes, like using iron to make fertilizer or using vanadium to make sulfuric acid. They're basically the secret engines driving the entire chemical industry.
So it's pretty clear, right? The way electrons are arranged in these elements isn't just some abstract thing you learn in a textbook. It's the direct reason we have materials and technologies we rely on every single day. And that leaves us with a big question for the future. As we push to invent better batteries, more efficient catalysts, and new sustainable materials, which one of these elemental superpowers do you think will be the next one we need to unlock?